an example that we have of a mid-ocean ridge is in the previous slide, as the Mid-Atlantic Ocean Ridge. So here we go. So here is the Mid-Atlantic Ocean Ridge expressed by the earthquakes that happen in that region. And we can see it really well in this image right here, right? So this is the ridge right there. So we know that a mid-ocean ridge, or at a mid-ocean ridge, we get new material, but we also know that the Earth's surface is not growing. So there must be locations within the Earth where material is being destroyed as well, not just created. So there is a type of plate boundary that causes destruction of plates at one of the plate's edges, so the destruction of part of the plate itself. So said boundary type we call a convergent plate boundary, and it occurs when two plates are moving towards each other. So places like this one above, you see the arrows coming towards one another, this being one of the plates, this being the other one right here. It is in these places where typically the more dense plate, which in this case would be the oceanic one, right? So we have seen that oceanic lithosphere is more dense than continental lithosphere. So we know that the more dense one will sink or will subduct below the less dense one, like we're seeing in the image. So here in the image itself, you see that the lithospheric mass from the plate subducting under the other plate, as you're seeing, the slab is going underneath. And such a location is called the subduction zone, as you're seeing here, labeled. So there is such a place near us. In fact, it's just a little bit west of us. It's in the northwest part of the U.S. So it's in Washington, Oregon, and the northernmost bit of California, where the Juan de Fuca plate is being subducted underneath the North American plate. And I will show you images of that later on. So at subduction zones, as I said before, the more dense plate will subduct below the less dense ones. And as you already know, again from the first section of the chapter, the oceanic lithosphere tends to be more dense than the continental lithosphere. So, if the two plates that are colliding or moving towards one another are one of oceanic lithosphere and one of continental lithosphere, then the oceanic plate will always sink, like what you're seeing here in the image. So, because there is creation of new lithosphere at mid-ocean ridges and destruction of lithosphere at subduction zones, the Earth's size actually remains overall pretty constant, never growing nor shrinking. So yes, there may be slightly more or less material at specific points in time, and that is witnessed by material that is stacking up in depth, or that is stretching out perhaps. But the overall size remains pretty constant throughout. Okay, what we're looking at here is a slide on sinking tectonic plates. So I talked about this already a tiny bit in the last slide when we were discussing subduction zones. But basically, when you have two plates that are colliding or converging, one of those plates will have to sink under the other, not always, but almost always. And the rule of thumb is that the denser plate will sink. So, from the image on the slide, we have an oceanic plate right here to the right, which is denser, and a continental plate on the left, which is more buoyant. The oceanic plate also happens to be younger because, as we have talked about in the last few slides, new lithosphere forms on one of its edges continuously, typically, and because by being denser it sinks below other plates without much time for it to mature. And it tends to be wetter and cooler as well. It literally contains more water, at least again in the closest areas to the surface. And it also has water that has been mixed within the sediments there towards the surface, towards the top part of the lithosphere, which again, are on top of the plate or on the higher area, higher section. And the water itself is mixed with other elements, basically. So, as your plate that is oceanic, more dense, wetter, and cooler is sinking, it plunges into the Earth at an angle. That angle at which it plunges relates to the density difference between the colliding plates. So if the density difference is too great, the angle would be greater. If the density difference is not so great, the angle would be a little bit shallower, okay? And as it plunges, the surface edge at which the plate meets becomes a deep cliff-like landform. So that would be right here. So the surface place at which the two plates meet, right there, becomes a cliff-like landform. Again, that tends to be not too far from the continental margin, right there, and that is called an ocean trench. Further below, as the leading edge of the plate comes in contact with very hot asthenosphere, so right here, parts of the plate, along with nearby and hot and less dense material, will actually start to melt and become magma in that section, which, again, as we have seen, the magma itself will later rise towards the surface and either cool before it reaches the surface, or it will erupt as volcanic material, as volcanoes, right? So two good examples of geographic locations on Earth where this happens are the Cascade Mountain Range, right? Where again the Juan de Fuca plate is subducting underneath the North American plate. And another very good example that you may be familiar with are the Andes Mountains in South America, where the Nazca plate is subducting underneath the South American plate. Another interesting thing to point out from this image is that as the ocean plate sinks, as you're seeing it sink, friction happens along the boundary of the plates as there is less and less space for both of those plates to coexist. And so they get cramped, or the material itself is cramped where everything is going to be. So this cramming of material causes earthquakes. It causes friction, it causes stress, so it causes earthquakes to occur. This type of plate tectonic boundary is where actually most of the earthquakes are experienced on Earth, as well as the strongest and the deepest earthquakes actually. Because the leading edge, as you're seeing, the leading edge of that plate slab is getting deeper and deeper the further that it goes away from the trenches, and as it's getting deeper, there's less and less space, and so more and more friction happens, which means more and more earthquakes occur. So, I've already mentioned this, but there are, hence, three main ways in which any two plates will move at plate boundaries. The first type is when they move away from one another, in which case new lithosphere is formed. The second way is when you have plates move towards one another, which is when typically you have lithosphere being destroyed. Again, typically is a keyword, often from the densest plate. And then the third way is when you have two plates that are sliding past one another. In this case, there's not going to be any lithosphere being created or destroyed, but there is lots of friction between the two plates as they do slide past one another. So we'll talk about the names for each plate boundary in more detail in the next coming slides. But again, those are the three motions: moving away, coming together, sliding past one another. Alright, so the table that I have here comes straight from your book, and it's excellent. It's a very good table, so I recommend that you go and view it as we go along the next few slides. But basically, it tells you the different types of plate boundaries that there are, those being divergent, convergent, and transform. So divergent, convergent, which is subdivided into three, and transform. The convergent one, again, is split into three depending on what type of lithospheric material is involved at the boundary, if it's oceanic or continental or both. So let's start with divergent plate boundaries. So divergent plate boundaries are typically found at the ocean, but not always. The plates here move away from each other, and so there is spreading of material and rising of new material from below to fill the gap. As we saw, the resulting landforms are usually mid-ocean ridges if the spreading occurs at the ocean, like the Mid-Atlantic Ridge, as I showed you before. And natural hazards that are associated with this type of boundary are typically light to moderate earthquakes. So that is right here in this column. Or you can also have effusive, or rather non-explosive volcanic eruptions. So we'll talk about the types of eruptions when we cover chapter 5, but for now just think of effusive or non-explosive eruptions similar to the ones that occur in Hawaii. Okay, convergent plate boundaries are of three different natures. When one of the plates involved in the collision is made up from oceanic lithosphere, there will be subduction. So in either of the cases where there is oceanic lithosphere involved, there's always subduction. If the boundary is between oceanic and continental plates, the oceanic one will subduct. If the boundary is between two oceanic plates, then the denser of the two oceanic plates will subduct. Both of the types of convergent plate boundary cases where you have subduction will cause a volcanic arc. So a volcanic arc is basically a chain of volcanoes along the plate that did not subduct. However, if the plate itself is continental, it causes a volcanic continental arc, like the Cascade Mountains. But if said plate is oceanic, meaning the plate that doesn't subduct is oceanic, it will cause a volcanic island arc, like the Aleutian Islands, which are a set of volcanic islands in Alaska that extend westward. And this is caused by the subduction of the Pacific plate underneath the North American plate. So I'll show you that in a few images later on. Both of these type of convergent plate boundary types cause very large earthquakes that are right here, and they also cause explosive volcanic eruptions. So like Mount St. Helens did some years back, for example. They're also related to tsunamis at times, and they are related to subsequent mass wasting and total subsidence from those events. A third type of convergent plate boundary happens when you have two continental plates that are converging. So here, when you have continental to continental convergence. In this case, there will be one of those plates that subducts, kind of, but because both of them are very buoyant, the subduction will be at a very, very, very low angle and at a very, very, very slow rate. Rather, what happens is that most of the material will simply collide and start building up in elevation and down in depth. So this causes massive mountain ranges. So a mountain range that is caused by this type of plate boundary is actually the Himalayas. So the Himalayas, as you know, are some of the tallest mountains, in fact, the tallest mountains that we have on Earth. And in this case, we have the Eurasian plate on the north that is colliding with the Indo-Australian plate on the south. So both of those plates are colliding, coming towards one another, and the material that is on either side is simply piling up and down in depth as well, forming these massive mountain ranges. So in this type of boundary, we also see great earthquakes, and typically we see flooding and mass wasting events that are associated with them. Lastly, we have the third type of plate boundary, and that is called the transform plate boundary. It happens when you have two plates slide past one another, and these can slide in either direction relative to one another. The result of this is typically earthquakes from the friction that is experienced by two plates rubbing, and often a change in topography with the movement of the plates. So a famous example of this type of boundary is one that actually happens here in this country, in California. As you may know, it's what causes the San Andreas Fault. In this case, the Pacific and the North American plates are sliding past each other. But another two good examples are one in New Zealand in the Alpine Fault, where the Indo-Australian plate and the Pacific plate slide past one another briefly. And then another good one is the Anatolian Fault, which happens in Turkey, where the Eurasian plate on the north and the Anatolian plate on the south kind of move sideways from one another. The Anatolian plate is a much smaller plate, so you might not see it in any of the slides that I have in this lecture.